Hello. This video is to accompany the lecture notes for the Diels Alder reaction to give you a little idea what's going on with some molecular models. So I have here 2,4-hexadiene with the methyl groups on each end and two double bonds in the middle. This one's showing all of the orbitals lined up. So this would be pi1, the lowest energy molecular orbital. And this is the S-trans isomer, where you see that the single bond here between carbon 3 and carbon 4 is the one that has free rotation. So if I rotate around that bond from the S-trans to the S-cis, you'll see that as I rotate it, I've broken the conjugation. So there's about a 6 kilocalorie per mole energy of activation barrier accompanied with breaking that conjugation and then reestablishing it. This compound is about 3 kilocalories per mole higher in energy than the S-trans version because of this unfavorable steric interaction between the hydrogens pointing towards the molecule. So this is the reactive molecule, right? It has to be in this S-cis conformation in order to interact with the dienophile. And what you can see, if I hold it in this particular rotation, is that it has that C2 axis of symmetry. If I rotate it around the bond, bisecting the molecule, the orbital hasn't changed. So it's antisymmetric, and this is pi2, where you have a node down the middle, right through here, and a change in the sign on the wave function. Here I have a Crowleyan. There's a carbonyl oxygen on this end, and this is the lowest unoccupied molecular orbital. This is pi3, which has two nodes, and therefore two changes in configuration or changes in sign on the wave function. So we have our aldehyde group here, and we have the two hydrogens that are cis to each other. In order for the diene to interact with the dienophile, the diene will have to come from either the top face or the bottom face. So if I interact these two molecules, you can see that the diene is on the top here and the dienophile is on the bottom. The interaction will be between these two end orbitals, one of which is blue and one of which is black, so they're out of phase with each other, and these two orbitals here, again, one of which is blue and one of which is black, so they're out of phase with each other. Okay. What has to happen for a bond to form is we need a bond between this blue orbital here, right, on the end, and this blue orbital here from the dienophile. And then simultaneously we need a bond from this black orbital to this black orbital on the dienophile. In order for the dienophile to form those two new bonds, it's going to have to rotate like this so that the top face is pointing directly towards the diene. Meanwhile, the diene is going to have to rotate so that these two lobes of these orbitals point towards the dienophile, which is here. This one's going to have to rotate this direction, and this one's going to have to rotate that direction. If I hold it end on, you'll notice that when I turn those, I'm turning those in opposite directions. That is what we call a disrotatory motion. So the two back carbons are staying put. I'm rotating this one down, and I'm rotating this one down. And the two methyl groups, which were in the outer positions, are going down, whereas the two hydrogens that are in the inner positions are going up. It will always be a disrotatory motion, and so you will always end up with a cis relationship in your six-membered ring product between the two groups that are on the outside, and a cis relationship between the two groups that are on the inside, hydrogen in this case. The complicated thing to think about is why this endo approach, right? The endo approach is where the dienophile comes in so that the carbonyl group sits underneath the molecule, as opposed to the exo approach, right, where the carbonyl group would be pointing away from the diene. The important interaction that stabilizes the transition state is between the carbonyl carbon, this orbital here, and the back end, or carbon 3, of the diene, right? That's not one of the ends of the diene, but it's carbon 3. With the endo approach, these two orbitals can come close together. You can see those two blue orbitals that are touching, if I get it in the right orientation, right? That's the secondary orbital overlap right there. we've got a new bond forming here between these two lobes, but we've also got secondary orbital overlap between the carbonyl carbon and the back end. In the exo approach, we would not have that. The carbonyl carbon is way over here, a long way from the diene. That secondary orbital overlap is what causes the endo rule and causes the endo substituent to end up going down, right? And so when you rotate the ends in that disrotatory motion and you form your six-membered ring, this carbonyl oxygen will be down, cis to the methyl group that was on the end. And you'll notice that all four of the yellow atoms are now pointing straight up. So that's the exo substituents on the diene ending up on the same side as the inner substituents on the dienophile. That's a stereoselectivity, not a stereospecificity. There's nothing that says that the exo approach can't happen. The exo approach is just less thermodynamically favorable because it lacks the transition state stabilization, the secondary orbital overlap here between the carbonyl carbon and the back end of the diene. It's stereospecific, though, with respect to the diene because the disrotatory motion is required by the transition state, which means the outer substituents will always end up cis. And it's stereospecific with respect to the dienophile because in the transition state there is still a partial pi bond here, which means that there's no free rotation about this carbon-carbon bond, and the substituents that are cis in the diene will remain cis in the six-membered ring. If you were to look at an inverse electron-demand Diels Alder reaction, now we're still in the S-cis orientation, but now we're working with the LUMO of the diene, which is pi 3 and has two nodes and therefore two sign changes. You'll notice that this is not a C2 symmetric orbital. This is a sigma symmetric orbital. There's a plane of symmetry down the middle of the molecule. The molecule itself doesn't have sigma symmetry, but the orbital has sigma symmetry. So this red lobe reflects into this red lobe, and this black lobe reflects into this black lobe. In the inverse electron-demand Diels Alder, we're working with the highest occupied molecular orbital of the diene. That's this one, right? And in this case, it's the HOMO, which is the pi bonding orbital. And again, it has sigma symmetry, right? Not the molecule, but the orbital. Because both of these orbitals have sigma symmetry, we have the right orientation for constructive interference on both ends of the diene-dienophile interaction where the two black lobes interact. You'll notice this is the EZ isomer of 2,4-hexadiene, where one methyl group is pointing in, that's a Z isomer around this double bond, and the other methyl group is pointing out. When we rotate this in the disrotatory motion, the methyl group that was pointing out goes down, but the methyl group that was pointing in goes up. In the six-membered ring product, the methyl groups will end up trans. There's no endo rule to talk about here because I don't have a substituent attached to this, but you'll notice that the trans relationship between the orange orbital and the atom and the yellow atom will be maintained as that simply rotates in to form the six-membered ring. So in the six-membered ring, right, we've got the two yellow atoms trans to each other, and we've got the two orange atoms trans to each other. That's because the inner atom will always end up trans to the endo, right, the endo substituent, and the outer atom will always end up trans to the exo substituent. If I add a methoxy group to this molecule, so now we have an additional methoxy group sitting on there. And I add a nitro group to this other molecule. Right? So now we have the nitro substituent on the back end on carbon 3 of the diene. And we have a methoxy group on carbon 1 of the dienophile. This molecule can approach either in an exo or in an endo orientation. If it were to approach in an exo orientation, it would look like this. If it were approached into an endo orientation, it would look like this. You'll see that I'm representing the lone pair on oxygen with this additional pi orbital here. One of the lone pairs on oxygen is part of the pi system. The other lone pair is in the sigma framework. The endo approach is once again favored. We're going to form new bonds between these two red lobes on the diene and these two red lobes on the dienophile. So those are the two new bonds that are forming. This rotatory motion, looking like that, forming a six-membered ring. And we're going to have secondary orbital overlap between this here, which carbon 4 of the diene, and the lone pair on oxygen. There's the secondary orbital overlap, which is stabilizing this transition state and causing the endo approach to be favored. The product, then, will have the methyl group trans to the methoxy group on the dienophile, because this methyl group was pointing in, right? And if it's pointing in, it will be trans to the endo substituent. The other methyl group will be pointing down and will end up cis to the methoxy group, because this methyl group here we're pointing out, and the outer substituent always ends up cis to the endo substituent. The 1,4 arrangement is preferred to the 1,3 arrangement, where the methoxy group would be up here on the same end of the molecule as the nitro group, because of the resonance structures shown in your handout. Hopefully that helps a little bit, seeing some models. I will also probably be posting a video where I draw some of this out on the board a little bit later on.